In section 10.3, we are looking at trig identities. Now, by the time you finish the A-level, trig identities will be something which you've spent a lot of time with and you've got stuck with a lot, but hopefully something which you are eventually able to deal with. Now, these two, we mentioned this in the first video on this chapter. If you look at the definition of sine and cos and tan, then you can see where these things come from. So sine squared plus cos squared equals 1, and tan theta is equal to sine theta over cos theta. I've used funny equal signs. I'll come back to those in a minute. Just in case you didn't watch the first video in the chapter and you don't feel like going back and looking at it, let's just quickly have another way of sort of getting an idea for kind of why this could be true. Sine theta is opposite over hypotenuse. So if I square that, I get opposite squared over hypotenuse squared. Cosine theta is adjacent squared over hypotenuse squared. Okay? And if I add those together, I end up with opposite squared plus adjacent squared over hypotenuse squared. And if you use Pythagoras theorem, you can see opposite squared plus adjacent squared equals hypotenuse squared, right? Just by Pythagoras theorem. So that is hypotenuse squared over hypotenuse squared, which is 1. So there's one way of thinking about it. And then with the tangent, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and if you do opposite over hypotenuse divided by adjacent over hypotenuse, that's the same as opposite over adjacent. And if you can't see that, just think of it this way. Adjacent over hypotenuse. Keep flip change, right, from, I don't know, year 9 timesing fractions or whenever we did that. Hypotenuses will cancel out. We end up with an opposite over adjacent. Okay, so there's another way of seeing it. Now, let's come back to this funny equal signs with the 3 lines if we've not seen that before. What it means is it's something like this. If I get 2x plus 3x, that is 5x. And I'd normally write an equals in the middle there. But let's think of something else. 2x plus 3x, let's write 5x equals 15. Now in this case, this is an equation. And we're saying there is one value of x that will make this work, and that's x equals 3. Okay? Now this one here, this is not an equation, this is an identity. This is saying that this expression is the same as this expression. There's not one value of x that will make the left-hand side equal to the right-hand side. Any value of x makes the left-hand side equal to the right-hand side. The right-hand side is just a different way of writing the left-hand side. And that's what we're saying here. Sine squared plus cos squared is equal to 1. It's the same thing. It's just a different way of writing 1. If you've got sine squared theta plus cos squared theta is equal to 1. So if you take the tan of an angle, then that is always the same as taking the sine divided by the cosine. There's no difference in the two. Okay, so that's what we mean by the identity. So with trig identities, what sort of questions are they going to ask us to do? Questions like this. Questions like sine squared 3 theta plus cos squared 3 theta. Well, it doesn't matter that this is 3 theta instead of theta. Let's relabel 3 theta and call it x. So this is sine squared of x plus cos squared of x. So it's equal to 1. Okay? It's the same thing. It doesn't matter as long as the thing that I'm inputting into the sine and the thing that I'm inputting into the cosine are the same. I'm going to get the answer 1. 5 minus 5 sine squared theta. Well, you can see that we can factorise this. And then we're going to use that sine squared plus cos squared is equal to 1. We can rearrange that and say cos squared theta is 1 minus sine squared theta. Okay? So 1 minus sine squared is another way of writing cos squared. So these new facts give us a way of rearranging algebra. We can still deal with all the usual stuff. We can still factorise or collect terms. But we have 2 new secret weapons which we can use, right? The sine squared plus cos squared equals 1 and tan theta equals sine over cos. What you've got to be aware of is as well as as this one being used straightforwardly, we can use it as cos squared and sine squared. We can kind of convert a cosine into a sine, right? So in part C, we do the same thing. We've got 1 minus sine squared of 2 theta. Well, 1 minus sine squared is the same as cos squared. So the denominator there, we can rearrange as square root of cos squared 2 theta. So that is sine 2 theta, excuse me, 2 theta over cos 2 theta, because cos squared and then square rooted is just going to give us cos 2 theta. And that is going to be the same as tan of 2 theta, okay? So we can use these new facts to solve all sorts of things and simplify nasty expressions involving sines, coses and tans. The other thing we can be asked to do is to prove an identity. And what that means is something like this. And you can take these questions to mean simplify that expression, but we're giving you a hint. When you've simplified that expression, it ends up looking like this. So don't think of this as an equation where you're going to balance both sides. Think of it as a simplifying question, but it's a show that. It's show that this can be rearranged to look like this. So bearing that in mind, the tip I've got for you is start with the side that looks the most complicated and try and simplify it. Don't start with the simplest side and try and complicate it. Start with the most complicated side and try and simplify it. The other bit of advice I've got for you on these is look at this and think of everything that you could possibly do, and do this at each stage. Don't just think, right, what shall I do next? Just think, well, what could I do next? What are my options? So here I'm thinking, well, I could split this up into a cos to the power of 4 divided by cos squared minus sine to the power of 4 divided by cos squared, and I could work that way. And if I did that, I'd have some sine to the power of 4 over cos squared, so some of the sines over coses could turn into tans, so that might work. I'm thinking, oh, I've got a difference of 2 squares on the top, so I could maybe use that. I'm also thinking cos squared could be turned into 1 minus sine squared, and here I've got a cos to the 4 and a sine to the 4, so cos squared plus sine squared, I've got cos to the 4 minus sine to the 4, so maybe I can make some cos squareds and sine squareds out of these things here. I'm wondering if I can factorise the top. I'm wondering if I can simplify, collect like terms, but I can't do any of those extra things. So those are all my options, okay? So explicitly think through all the things that you could possibly do, however sort of silly they seem. Think through them, because if you get into the habit of thinking through all the possibilities, if you get stuck, you can go back and you've already got a plan B ready. Okay, what they've done in the example here is to use the difference of 2 squares trick first, and that, of course, because it's in the example, that's the one that gets us to the answer. But if you tried splitting this up into 2 separate fractions first and found that didn't work, but you had thought at first, well, maybe I could do something by factorising the top because it looks like a difference of 2 squares, then you've got your plan B ready. So as soon as you get stuck, you can go back and try plan B and see if that works. Now, there's no need for me to kind of go through these. Look, difference of 2 squares on the top, cos squared plus sine squared equals 1, cos squared minus sine squared over cos squared, split that up into 2 separate fractions with the same denominator. Cos squared over cos squared is 1, sine squared over cos squared is sine over cos, all squared, so that's tan squared. So that's what we were trying to do. We will get stuck on these. If not on the AS level book, you will get stuck on the A level book. They're nasty, but the process of getting stuck is the process of learning. So the biggest bit of advice I've got for you is don't go to solution banks too soon. Get stuck on it, give it 24 hours, come back to it, try it again. If you've spent a long time not being able to do a particular question and you've gone and tried other questions and you've come back to it and you're still stuck again, then at that point, talk to a teacher or talk to a friend and get them to explain it to you and talk you through it. If you really can't find somebody and it's really frustrating you, then finally at that point, maybe think about looking at a solution bank. If you go to a solution bank too early, if you get stuck and 2 minutes later you just check on the solution bank, you're cutting short the process of trying to solve the problem, and that is cutting short a really important part of the process of learning. So you might understand all the answers, but you're not going to be able to do it yourself as well in the long term. So don't panic if you're getting stuck. It's a necessary part of the learning process. It feels uncomfortable at the time, but it will help your longer term memory. Last thing to do is example 8. And this is another one of those where I'm going to do this without any reference to cast diagrams, but with the use of the graphs. In fact, I think I'll do this in a separate video because they are interesting little examples.